So we will now begin our first chapter, the first topic, namely the notion of a measure in an abstract setting. So recall, measure is supposed to generalize the notion of length, area, volume, etc. depending on the dimension. And when calculating complicated areas, what did we say people did? Namely, you break it up into smaller domains, add some areas, subtract some areas, and so on. So when we want to define a measure mimicking the properties of area, volume, or length, so we need to do it on a class of subsets. If we can do it on all subsets, it's fine, but very often we may not be able to do that. So we will restrict ourselves to a class of subsets. So when you want this class of subsets on which you want to define, so you want to add areas and subtract and so on, that means you have to be able to put together sets and you should be able to take away some sets. And that leads us to the following set. So the class of sets on which we will define the measure, so we want to look at that. So first section will be Algebra of Sets. So throughout we will work with a non-empty set. X is a non-empty set, and we will denote the power set of X. This is the power set, and this is a collection of all subsets of X. So this notation we will always use. So we will define, so we'll start with a definition. A collection R of subsets of X is called a ring if it is closed under formation of unions and differences. So because we wanted to put together sets, we want to take away some sets and so on, and therefore where the measure is going to be defined should be defined on a collection which is closed under these operations. That means if EF belong to R, then this implies that E union F should belong to R, and also E difference F belongs to R. Okay, this is the difference of set theoretic difference of the two sets. If X belongs to R, then the ring is called an algebra. So the algebra is nothing but a ring where the whole set itself belongs. So okay. So now we have a series of remarks. So remark. So by induction, closed under finite unions. Then 2, you have that empty set always belongs to R, always. Because if E belongs to R, then phi is nothing but E minus E, and therefore it should belong to R. It's closed under differences. 3. So if E and F, so R is a ring, and E and F belong to R, then the symmetric difference E delta F. So what is the definition of E delta F? This is E minus F union F minus E. So you have two sets E and F here. So this is E minus F, this is F minus E, and this of course will be E intersection F. Okay, so you have that E delta F is called the symmetric difference. That also belongs to R, because you have E minus F is in R, F minus E is in R, and therefore the union of elements of R is also in R. And also, what is E intersection F? E intersection F is nothing but E minus F, and therefore this also belongs to R. This belongs to R, and then difference belongs to R, and therefore you have that E intersection F. So the ring is also closed, so implies R is closed under intersections, and by induction this is finite number of intersections are also true, and symmetric differences. Okay, then for conversely, if R is closed under the symmetric difference and differences, and if it's closed under and unions, then it is a ring. Because if E and F belong to R, we already know it is closed under the union, so E union F belongs to R, and then further E minus F can be written as E union F delta F. So just check this, E minus F is nothing but E union F delta F. You can just look at this picture and you will immediately see that that is true. Okay, so you have this, and therefore this belongs to R as well. So if it's closed under symmetric differences and unions, then also it is a ring. So this is the equivalent statement. So if R is closed under delta and intersections, then it is a ring. Because if E and F belong to R, then E delta F is nothing but E union F is nothing but E delta F delta E intersection F. So it is closed under intersection, so this belongs to R. It is closed on symmetric differences, so this belongs to R. And then you have two elements of R, and the symmetric difference is also in R. And then E minus F equal to E union F delta F we already saw. E union F we just proved is in R, and then delta is already, okay, it's a closed operation, and therefore this belongs to R. So these are, okay, then one more remark. So if R is an algebra, so implies R is closed under unions and complementation. Okay, so EF belongs to R, so then you have E union F is also belongs to R, that is true, and you have E is in R, then X is also is in R, so X minus E, which is nothing but E complement, so this is the symbol for complement which we will use, E complement belongs to R. Conversely, R closed under unions and complementation implies it's a ring, because if you have E is in R, then E complement is in R, and X equals E union E complement, so this belongs to R. So R is already there, it's closed under the unions. And then what about the differences? E minus F is nothing but E intersection F complement, which is equal to E complement union F whole complement. Okay, so all these operations are R operations, so this belongs to R. So it's closed under the unions, X is there, and it's also so this is not just a ring, it's a algebra closed under the unions, closed under differences, and X is there, so this becomes an algebra. Okay, so we have various alternative ways of defining a ring or an algebra, and these are all very easy to state using set theory. Okay, so now let us see some examples. So the first example are the trivial ones. So you take R equals just one thing, namely empty, or you take R equals the power set of X, are rings. In fact, this is an algebra. Okay, so these are the trivial examples. So second example, slightly non-trivial. So Z equals X. So Z is a set of all integers, and then you take R to be set of all A contained in Z, such that A is non-empty and finite, or A is empty. Okay, so then R is a ring. Okay, that's because you either have empty set or you have a finite subset, non-empty subset. So if you take two finite non-empty subsets, their union is again finite, and therefore it is closed under the unions. And if you take the difference of two finite subsets, well, it may be either empty, which is already there, or it will be a subset of E, which is already finite. So it's going to be a finite set, and therefore will belong to R. So this is closed. This is very trivial again, but it's a good example. Okay, so the next example which you are going to see is a very important example, because this is where this is the starting point of the construction of Lebesgue measure, which we will see later on. Okay, so we are going to start with this example. So let us take X equal to R. So that is our basic set, and then we will define P. This is to be set of all semi-closed intervals, left closed, right open intervals, such that AB is in R and A is of course less than or equal to B. So if A equals B, then the convention is that AB, so this is closed and open at B, so this means this is, by definition, this is the empty set. Okay, so this is the idea. That's why I have written A less than or equal to B. Okay, so then you take R equals collection of all finite unions of members of P. So R to be the collection of all finite unions of members of P. So obviously R is closed under the unions, because you take two finite unions and put them together, you are going to get another finite union. So there's nothing to do. So only we have to check about differences. Now if you take AB minus CD, so there are various possibilities. Okay, so this will be either AB if intervals are disjoint, okay, and it's equal to empty set if AB is contained in CD, okay, and then if A is less than C, less than or equal to D, less than B, less than or equal to D, Okay. Then you have AB minus CD. So you have AB, and then C is between somewhere here, and D is here. So AB minus CD is nothing but AC. And it is equal to, so if you have that A is less than or equal to C, less than D, less than B. So if both A is here, then C, then D, then D, then AB minus CD is nothing but AC union DB. Okay. And if you have that, if C is on this side, if C, then you have A, then you have D, and then you have B. Okay. In this case, you will have this equal to AB minus CD will be nothing but DB. So whatever kind of difference you take, you are only going to get another, either the same thing or a union of such intervals. And therefore, now if you take any finite unions, they will be again combinations of these sets, and therefore this implies that R is closed under differences. And therefore this is a ring. Okay. No, and also remark, every element of R can be written, we know it's written as a union of members of AB of P as a disjoint union of members of P. So you would have AB, and then so this is A here and this is B, and then you have say C and D here, and then you, so the union of these two is nothing but AD, and therefore AD you can write as AC union CB union BD. Okay, so these are all disjoint members of P, and so this way anything can be broken up and written as a disjoint union. Definition again. So a collection S of subsets of X is called a sigma ring if S is a ring and closed under countable unions. So we have, if EI belong to, so EI, I equals 1 to infinity, EI contained in belongs to S, then you have that union I equals 1 to infinity EI belongs to S. And of course difference is, so it's already a ring, so S is a ring and it is closed under the countable unions. S is called a sigma algebra. So this is the object which we will really study throughout this course. Okay, S is a sigma algebra if it is a sigma ring and X belongs to S. Whenever you want an algebra, the whole set must belong to it. So throughout this course, you will find this, we will put this sigma in front of some definition, then we will mean that something countable is allowed. whereas previously only finite operations were allowed. Now we are going to use countable operations. Okay, so countable unions will be allowed, and that is what we have this. Okay. So if, remark again, so sigma ring is a ring formed closed under countable unions. Okay, now if you take EI is a countable collection, what is intersection EI? I equals 1 to infinity. That's equal to, you can write as E minus union I equal to 1 to infinity E minus EI. And each of this belongs to S, difference belongs to S, so this belongs to S, where E is nothing but the union I equals 1 to infinity EI, which belongs to S. Okay, so it is closed, so implies closed under countable intersections as well. So in the same way, sigma algebra will be closed, you can define it this way, under countable unions and under complementation. So this will give you a sigma algebra. Okay, so now finally let us take XE, an arbitrary collection of sets, of subsets of X. Okay, so then of course E is contained in P of X, which is of course at the same time a sigma ring, and also it's a ring. Okay, it's a ring, it's a sigma ring, whatever you want to say. Now intersection of rings is a ring, obvious. So you take various rings, take the common elements of these rings, common subsets. Now if two elements are in this common subset, then the union is in all of them, and therefore it's in the intersection. Difference is in all of them, and therefore this. Similarly, intersection of sigma rings is a sigma ring. For the same reason, you take a countable set in the common collection, then countable union is going to be in all of them, and therefore it will be in the common one, and then differences are also there. So intersection of ring sigma, and always you have power set is a ring or a sigma ring which contains this. So you can take the intersection of all rings containing E, or the intersection of all sigma rings containing of E, and that will be a ring, that will be, so there exists smallest ring or sigma ring containing E. So this is called the ring or sigma ring generated by E. So, and then the notation for this is, if it's a ring you have R of E, and if it's sigma ring we will call it S of E. So this will be, given any arbitrary collection of sets, we will choose the smallest ring which contains it, and or the smallest sigma ring which contains it, and that will be called RFE or SFE. Okay, so this is the basic definitions. So we will now we have seen some examples. So next our aim is to construct a measure on a ring or a sigma ring. Okay, so that is what we will do.